Why the Spruce Goose was impossible to fly. Opening hook, the constraint. Visual, black and white footage of the massive H-4 Hercules rolling across the water. Cut to scale comparison with modern aircraft. In 1947, the largest airplane ever built lifted off the water, flew for 26 seconds, and never flew again. It had a wingspan longer than a football field. It weighed 180 tons. It carried 8 engines. And according to many engineers at the time, it should not have flown at all. On paper, the physics didn't make sense. The aircraft was too heavy. Its materials were too weak. Its drag was too high. And its engines were too underpowered. So why did Howard Hughes build it? Why did the U.S. government fund it? And why, despite technically flying, was the Spruce Goose fundamentally impossible as a practical aircraft? To understand that, we need to start with a simple equation, one that governs all flight. Visual, lift equation appears on screen. L equals 1 to rho v to SCLL equals \frac 1 2 \rho v squared S underscore L equals 21 rho v to SCL. Lift equals 1/2 air density times velocity squared times wing area times lift coefficient. This equation doesn't care about ambition. It doesn't care about patriotism. It doesn't care about government contracts. It only cares about physics. And physics was not on the Spruce Goose's side. Keycap won the context. Why build it? Visual, World War II convoy footage being attacked by German U-boats. During World War II, German submarines were sinking Allied cargo ships faster than they could be replaced. The Atlantic became a bottleneck. Shipping troops and tanks across the ocean was deadly and slow. The solution? Fly them. Not 10 soldiers. Not 50. But entire battalions, 750 fully equipped troops in a single trip. This required something unprecedented. A flying cargo ship. The U.S. government contracted industrialist Henry Kaiser and aviation innovator Howard Hughes to build it. The requirements were extreme. 750 troops, 2 Sherman tanks, 60 tons of cargo, transatlantic range, built without aluminum, reserved for fighter production. That last constraint changes everything, because airplanes are limited not by dreams, but by weight. Keycap 2 the physics constraint, the tyranny of weight. Every aircraft fights one enemy, gravity. To stay airborne, lift greater than or equal to weight lift / Jack weight lift greater than or equal to weight. If the aircraft weighs 180,000 kg, it must generate at least 1.76 million newtons of lift. That means either increase speed, increase wing area, increase lift coefficient. But here's the problem. Large aircraft scale poorly. When you double an airplane's size, volume, and weight increases by a factor of 8. Wing area increases by a factor of 4. Visual, cube-square law animation. This is the square-cube law. It is one of the most brutal constraints in engineering. As aircraft get bigger, they become proportionally heavier faster than they can generate lift. The Spruce Goose had a wingspan of 97.5 meters, even larger than a Boeing 747. But unlike a 747, it wasn't made of aluminum. Keycap 3 materials science. Why wood was a disaster. Visual, close-up of laminated birch layers. Despite the nickname Spruce Goose, it was mostly birch plywood, because wartime aluminum was restricted. Now wood is surprisingly strong for its weight, but it has 3 fatal flaws. It absorbs moisture. It suffers from fatigue. Its strength-to-weight ratio is inconsistent. Modern aircraft aluminum alloys, like 7075 T6, have a tensile strength around 500 MPa. High-quality birch plywood, roughly 40 to 60 MPa. An order of magnitude difference. An order of magnitude difference. Ernal bracing, which increases weight, which requires more lift, which requires more wing, which increases drag, which requires more power. This is the spiral. Keycap 4 aerodynamics, the drag problem. Visual, CFD airflow over massive wing. Drag increases with D equals 1 to rho v to SCD equals \frac 1 2 \rho v squared S infinity equals 21 rho v to SCD. The Goose had enormous frontal area, 8 radial piston engines, external bracing structures. At cruise speed, 250 km/h, drag would have been immense. Now compare that to modern jets. A Boeing 747 cruises at 900 kilometers per hour. Why so fast? Because drag increases with velocity squared? Yes. But flying faster allows smaller wings. Smaller wings reduce structural weight, reduce drag, increase efficiency. The Spruce Goose couldn't fly fast because piston engines limited power output. Each Pratt & Whitney R4360 engine produced 3,000 horsepower. 8 engines gave 24,000 horsepower. A Boeing 747? Over 60,000 horsepower equivalent per engine, times 4. The Goose was underpowered. Not completely incapable of flying, but incapable of flying efficiently. Keycap 5 The hero moment. How it actually flew. So how did it lift off? Ground effect. Visual. Diagram of wing close to water surface compressing air. When a wing flies close to the surface, high-pressure air beneath it cannot dissipate downward. Lift increases. Induced drag decreases. The Spruce Goose flew at about 70 feet above the water. It never climbed higher. It essentially skimmed the surface. In other words, it flew in the most aerodynamically forgiving condition possible. Remove ground effect, and the required power increases dramatically. This wasn't a proof of viability. It was a demonstration of possibility. Very different things. Keycap's 6 structural limits. The wing bending problem. Visual. Beam bending diagram showing stress distribution. Long wings are efficient, but they bend. The bending moment at the wing root scales with weight times wingspan weight backslash times wing backslash span weight times wingspan. The Goose had a 97.5 meter span. That creates enormous torque at the root. To prevent failure, engineers reinforced the wing spars heavily. More reinforcement equals more weight. Modern aircraft solve this using aluminum alloys, titanium fittings, carbon fiber composites, wood, not ideal for sustained cyclic loading. Repeated Atlantic crossings, structural fatigue would have been a serious risk. Keycap 7 Economic reality, why it could never work. Let's do comparative math. The H-4 cost approximately $23 million in 1940s dollars. That's over $300 million today, and it flew once. For the same cost, the U.S. could build dozens of Liberty ships, each capable of carrying 10,000 tons, across oceans, reliably, without aerodynamic risk. Aircraft only make economic sense when speed offsets cost. But piston-powered flying boats were slow. Jets changed the equation in the 1950s. Higher speeds, pressurized cabins, aluminum structures. The Goose was built at the exact wrong moment in history. Too late for piston era. Too early for jet age. Debunking the myth. Was it truly impossible? Here's the important nuance. The Spruce Goose was not physically impossible. It did fly. But practical aviation isn't about whether something can fly. It's about whether it can. Fly efficiently. Fly repeatedly. Fly safely. Fly economically. By those standards, it was nearly impossible. Because every design choice amplified a trade-off. Bigger wings, more bending, more weight. More weight, more power, more fuel. More fuel, more weight. Wood structure, more reinforcement. More reinforcement, more drag. There was no escape from the physics loop. Keycap 9 Modern comparison. Could we build it today? With carbon fiber composites? High bypass turbofan engines? Fly-by-wire stabilization? Yes. In fact, we already have something larger. The Stratolaunch aircraft. Visual, Stratolaunch comparison graphic. Wingspan, 117 meters. Composite materials. 6 jet engines. But notice something. It carries rockets. Not tanks. Not 750 troops. Because cargo aviation economics still favor ships. Ships are slow, but incredibly efficient. Airplanes are fast, but extremely expensive per ton-kilometer. Physics hasn't changed. Only materials have improved. End arrow the verdict. The Spruce Goose was not a scam. Not a fantasy. Not purely political theater. It was an honest engineering attempt to solve a wartime logistics crisis. But it violated too many scaling constraints at once. The square cube law. Material limitations. Engine power density. Drag growth. It flew once because of ground effect and careful piloting. But it could never have become a practical transatlantic cargo solution. Nature sets limits. Engineers find workarounds. But sometimes, the workaround is to wait for better materials and better engines. The Spruce Goose wasn't impossible. It was premature. And in engineering, Timing is everything. Hashtag